going alive. Now we are alive, okay? So thank you very much, everybody, to be here in this channel, Paleobot videos, Paleobotany and Palynology.
So thank you very much
for everybody.
To be here in this channel, Paleobot videos.
It's a pleasure for me receiving Dr. Gregory Retallack. Sorry, any problem are here. I think 1 minute. Let me see what is happening. I don't know what is happening here. 1 minute. 1 minute. Any problem here? Hello? Are you listening? Please click in your microphone. Yes.
Yeah, it's
Are you
okay.
listening?
Yeah.
Okay. So please, you close every window open in your computer because it can interfere. Okay. So is it. Also, thank you very much, everybody, to come here in my channel, Paleobot Videos, Paleobotany and Palynology for everybody. It's a pleasure receiving here Dr. Gregory Retallack, a very important scientist, okay? The author of the book Soil of the Past. Nowadays, Dr. Gregory Retallack is professor in the Department of Geology of the University of Oregon. And he is director of Codon Fossil Collection in Museum of Natural and Cultural History in University of Oregon in Eugene. And here we have also today Dr. Marcos Gervásio. Dr. Marcos Gervásio is a professor in Rural Federal University of Rio de Janeiro. He is an important scientist also here in Brazil. He worked with soils. And nowadays, he is professor in this university. And he has more than 200 papers published in important articles. So, very important scientist here in Brazil, Dr. Marcos Gervásio also. So it's a pleasure for me receive these two important scientists in my channel. Sorry, not in my channel. This channel is a extension project here in Brazil. And this project is of Rural University of Rio de Janeiro. So now I will give the word to Dr. Marcos Gervásio, and after Dr. Gregory Retallack will talk more about his curriculum, about his experience, and after we can start the presentation. Okay? So please, Dr. Gervásio, you can talk now. You can talk in Portuguese if you are more comfortable. But listen, many people around the world are listening us now. Not only people from Brazil.
Okay, so thanks, Sarah. Thanks, Dr. Greg, for accepting the invite of Sarah. I will talk in Portuguese and in English because I'm more comfortable in speaking Portuguese. Eu sou professor, I'm professor of Rural University of Rio de Janeiro. Sou professor da Universidade Federal Rural do Rio de Janeiro, and I'm working with soils. And in the last years, I have been working with paleosoils and proxies. Nos últimos anos, eu venho trabalhando com paleossolos e indicadores de mudanças paleoambientais, especially with soils especialmente com solo orgânico nas regiões sul e sudeste do Brasil, and south and southwest regions in Brazil. And we have been found important results that, and I think these results will contribute to give more information about how these soils was formed in the past. Então, nós estamos trabalhando com esses solos, especialmente com solos orgânicos, e principalmente com fitólicos, outros indicadores, tentando uma reconstituição paleoambiental. Então, eu gostaria de agradecer a presença do professor Greg. I would like to thank Dr. Greg to accept the invite of Sarah to talk with us here, to make this presentation. And passo a palavra para você de novo, Sarah. Thanks.
Okay. So, thank you very much for your presentation also, Dr. Gervásio. So, Dr. Gregory, you can talk a few minutes about your experience, okay, about your curriculum, your experience, and after we can start your presentation, okay? Please, introduce yourself. Introduce yourself.
Very good. Thank you, Sarah and Marcos. I appreciate it. Let me share the screen.
Okay. I gave you yesterday the step-by-step to do
there
this.
There it is.
Yes, it's here. It's here. It's here. I will add 1 minute. Yes. Okay.
So, my name is Gregory Retallack, and I'm a professor here at the University of Oregon. I've been here for 40 years, and it's been really quite marvelous. I was hired as a paleobotanist, and it was really quite lovely to run into Sarah at the Berbulsani Institute of Paleobotany in 2014. Seems like such a long time ago. We hit it off there quite well, and I was really pleased to be invited to be able to share some research which I've currently completed and which I'm really quite excited about, the discovery of fossil plants that fill a big gap in the evolution of plants. The big problem with the fossil record of plants, of course, is that most people have the idea that there was no life on land before the Silurian. Here are some quotations, for example, from some textbooks and from a recent paper. And the basic idea, and you still see it in reconstructions of the history of life, maybe by David Attenborough, among others, there's these barren landscapes before the Silurian. The problem is that we know that there has to have been something there because we have evidence from palynology and also from fossil soils or paleosols, which are my own personal specialty. But sadly, until recently, we haven't been able to actually find the fossil plants. So what was before the forests of the Carboniferous and before these herbaceous plants of the Silurian? It's a very interesting question indeed. What I want to talk about today are these 5 steps in the colonization of the land, which was far from barren, even as far back as the Ediacaran. Ediacaran plants have been found. They're not actual land plants. They're more like lichens, but some people like to call these sorts of things plants. They certainly would have looked like plants. The land was greened a long time before the Cambrian evolution of non-vascular plants, which we know already from palynology, and the Silurian advent of vascular plants, the the Silurian advent of lichens that are more like the lichens that we have today, and the Devonian advent of trees. So this is a sort of an outline of my talk today. I'm most excited about a paper that just recently came out in the journal The Paleobotanist, which is published by the Birbal-Sahni Institute of Paleobotany, a discovery by me of a fossil site which has been known for a long time, since 1942. It was actually excavated during the construction of this dam, which is called Douglas Dam, which is in eastern Tennessee, not far from Dolly Parton's theme park, Dollywood, which I'll talk a little bit more later. At the pylon that you can see at the other end of the dam there was a hole dug down in there to set that footing for the dam itself, and it excavated some rather wonderful fossils. The map that was made at the time of this hole, here it was filled with sediment. This is the limestone. It appears to have been an ancient paleocast. This is overburden right here. Here's the paleocast. Here's some of the breccia that fell down. Here's some green tuff. And then the plants are in this layer here of silty dolostone, which was one of several of these dolines, or deep karst depressions, in the Middle Ordovician Douglas Lake member of the Lenoir limestone in this part of Tennessee. This sort of paleo environment I can envisage very, very well. I don't know if you've ever been to Cancun. We went there on a visit to Cozumel to go skin diving, but a pretty classic tour from Cancun to Chichen Itza is to stop off at this wonderful doline, which is called Il Quil. It's a deep freshwater doline, about 20 meters thick, just like the one in the Ordovician. And you can see in this particular area of tropical rainforest, it's quite heavily vegetated with plants draping off the walls and down into a pool at the bottom, which also includes some exposed surfaces. The locality is quite famous for these fossils, which were described in 1956.
Dr. Retallack, 1 minute, 1 minute. Are you passing your slides or not? Because if you are passing, it is not appearing here. It is not appearing here. You have to share it.
Yes, I'm on slide 4.
No. So you return it because it is not appearing here. Okay, you have to click. Yes, now yes. Now yes.
I don't think I can use the slide function. Well, to return, here's the question as I set it up. Here are the 5 questions that I hope to address in this lecture. And here's the site, which I'm very excited about, at this end of the dam here, where there was an excavation which revealed fossil plants in a layer right here. This is a cross-section. This is a horizontal section through this doline, this ancient karst depression in the top of the Lenoir, top of the Mascot Dolomite, and covered up by the Lenoir limestone, which dates these fossil plants as 460 million years. This is what the modern environment was like, I think. This is usually included on an itinerary, the mass tourism itinerary from Cancun to Chichen Itza. And the locality is quite famous for these fossils of arthropods, 2 unusual articulated arthropods, which were described by Castor and Brooks in 1956. But the excitement of this locality for me is not these arthropods, but rather these fossil plants. I have a whole bunch of new species that were described in the journal in the Paleobotanist that reveal what plants actually looked like in the Middle Ordovician. This is one which I named Castalorum crispum after Kenneth Castor, who originally obtained the collections from the dam construction. Here's a sketch. Here's what the actual fossil looks like. Here's a spore and elater. This is an early hornwort, and it's very, very similar to the modern hornwort, Leosporosauris ducii. Here's an involucre here. Here's the sporophyte, which in the case of Castalorum crispum tended to split and furl back. Here's the thallus right here. Laesporosceus is a very unusual hornwort because it has smooth, small spores. And this is why palynologists have been mystified for so many years as to why there's so little record of hornworts in the Ordovician fossil record. We now have them. Laesporosceus lives in Panama now, and it's among the most primitive of the living hornworts. Another new species, this was a species that was actually named by Ken Castor. He called it Cystites mirabilis. And this is the holotype right here, this one. He thought that perhaps it was a stenophore, or a sea gooseberry, or sea jelly, a marine fossil. However, ctenophores have a comb which will never flop over itself like a piece of a noodle. And we found other specimens in the same collection which show the reproductive structures, which are very clearly like a modern liverwort. Archegoniophores and antheridiophores on a thallus which is fairly sparsely branched, but you can see a bit of a branch here. The spores are pretty similar to those of modern liverworts as well. And spores like this have been noted before by palynologists. One of my favorite plants from this assemblage is this spatter of carbonaceous material. This is my sketch of it. There are individual clusters here, 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 and here, which I believe is a balloonwort. Balloonworts have a very interesting spore tetrad shape. Here's the tetrad right here. This is a tetrad which I've named Jane Greyer Sibylla. Jane Greyer found these tetrads. She called them tetrahedrolites, and she argued that these indicate that in the Ordovician, and perhaps even as far back as the Cambrian, according to Paul Strother, there may have been these balloonworts, these very inconspicuous plants that are very similar to the modern Sphaerocarpus. Here's a modern one here. There's an involucre which surrounds a whole bunch of these spores. Here's a spore mass. Here are the involucres of an individual one in a scanning electron microscope. Sibylla, of course, means Sibyl or prophetess. Jane Greyer was right. These spores, which are so similar to the modern balloonworts, now are represented by a fossil species named in her honor. Easy to miss, a very tiny plant. I've been searching for them around Eugene here in the springtime for quite a number of years and not been able to find them. We also found mosses, and I was very pleased to be able to name one after Dolly Phyton. Her Dollywood amusement park is not far from this site. And a rather classic radio lab, which is one of my favorite radio shows here in the US, show was Neon Moss, after the neon moss that lives around Dolly's mountain home in Tennessee. Dolly Phyton is an extinct taxon, which has leaves that have toothed margins. They're very, very small. This is about 2 millimeters across. Sorry, I didn't put a scale on that. But here's a sketch of this specimen here, which is the type specimen. The spores are small and relatively smooth. The closest relative to Dolly Phyton is a peat moss. Peat mosses have capsules that are on a fairly short stalk and erect on the same axis as the main axis. There's a second moss too. This one's very distinctive. It has rather small leaves and it has recurved capsules. Here's an SEM of the capsule. It has tiny little spores which are heavily ornamented for their size. And I was very pleased to be able to name this after Diane Edwards, who's been a pioneer in studying early land plants. A comparable modern moss is Brian miniatum. I believe this was a harsh moss, not a peat moss. These are still fairly basal in the family tree of mosses. But even more exciting in this assemblage is there's fairly clear examples of mycorrhizae, of the kinds of fungi that live associated with the roots of plants, and that also are known to be associated with early bryophytes like liverworts and mosses. In fact, many of us think that land plants could never have colonized the land unless they were in symbiotic association with mycorrhizae. Here's one, a new species. I named it after Paul Strother. Here's the spore itself. Here's an arbosel, which would be penetrating a cell. Here's an isolated spore. Here's an SEM of the spore, which shows this unusual ornament, which distinguishes this as a different species. Here's a living one, a modern Glomus chloradius, this one right here, a beautiful photo by Yolanda Dalpay. Mycorrhizal fungi, we know, go back to the Ordovician from isolated spores, and now we're finding not only the spores, but also the arbosels. And then finally, in this assemblage, a good old friend of mine, Prototaxis, which I worked on quite a bit, and I'll talk a little bit more about that, but I was very pleased to find Prototaxis in this assemblage. It's a funny-looking creature. I hesitate to say plant because it's not really a plant. It's a fungus, pretty clearly, and I believe it is a lichen. I was very pleased to name this species after Rosemary Honegger, who's been a lichen specialist for quite a number of years. This is a photograph of the haustorial hyphae in the background, and this is the symbiont. The symbiont is coccoidal, meaning it's kind of circular, and it's attached by the haustorial hyphae in here. This means it was a lichen which had an alga as its photosymbiont. The details of the fungal component of this lichen are aseptate, and I believe these are actually glomalian lichens or mucoromycotonin lichens, but not the same as the mycorrhizal lichens, mycorrhizal fungi that we find in the same deposit. So here's a reconstruction of this assemblage in the Douglas Lake member of the Middle Division of Tennessee. We have these hornworts with the horns in here. We have these Jane Greyer, these balloonworts clustered on the ground here. We have two kinds of mosses, Edwards phyton and Dollyphyton, and these wonderful tall lichens. And when I say tall, well, most of these plants, of course, are ground-hugging plants, as are liverworts today. And the size of the stem of Prototaxis is actually about the size of a pencil. But that's pretty giant for the Ordovician. We have evidence also that these were growing fairly thickly, but I'll get to that in a bit. Here's another site for Prototaxis. I was able to study this wonderful specimen called the Shunamong Tree, which is in the New York State Museum some years ago, and it appears to be the same species, the type species of Prototaxis. It's middle Devonian. It's in the Belleville sandstone, with my colleague Ed Landing at the New York State Museum. Fantastic tree. It was actually first excavated by a farmer who at Ogden Cooley, who excavated it completely in 1870. And he was very keen in noting that the trunk, which is here, had branches, at least two at the top and then several at the side. And each of these branches were about a meter or so in length. The total length of the tree that he measured and excavated in the quarry there was about 9 meters long. The part that's preserved in the New York State Museum still is just this upper part of the trunk here, and then the base of the branches, which you can see here. You can see there's a divergence between the apical branches, this one here going this way, this one here going this way, and there also are branch styles back further down on the trunk where you can, so that you can reconstruct that this was a tree which was tall and branching. Now, people have wondered about the histology of Prototaxis. This particular tree, the Shunamong tree, was permineralized. These sections are from a paper that was written many years ago on the histology of it, identifying it with Prototaxis loganii, which is better known from the Middle Devonian of Quebec. And here's my reconstruction of its histology. I was very excited to find in the bark of this particular example what appears to be a coccoid, an alga, which is surrounded by hyphae in a haustorial arrangement. And these occur within cortical nests. The cortical nests have the algal photobiont in the outer part of the trunk, but of course not in the inner part of the trunk. This was a fungus that formed growth rings, and obviously the shading effect of this extra growth ring would mean that these algae would no longer work. It's possible that they were actually shunted out with the growth of this extra ring from a basal Protothallus as the rings of the tree grew. This is a tall tree now, almost 10 meters or so, with quite a girth at the base, and was a substantial part of the vegetation of the Middle Devonian. So substantial, in fact, that even on the Middle Devonian, we did have some vascular land plants around. It towered over them. Here are some reconstructions of Prototaxides by various authors. This one by Graham et al. Is not favored, but it's an interesting idea. She thought that perhaps it was just a rolled up mat of early land plants, of non-vascular land plants. But the histology is clearly fungal. It has those aseptate hyphae of probable Mycorrhizal or Glomeromycotin algae. Here's the original one that Dawson proposed in 1888. Very similar to my reconstruction here of the Shunamong tree. Schweitzer had other specimens in Germany, which he reconstructed this way as a flexuous kind of an alga. This is my reconstruction of Mozillophyton. And then there's another one that has kind of leafy blades, which is called Germanophyton. There are a variety of these kinds of plants in Devonian floras. They are not plants. They are actually lichens, tree-sized lichens, which have a symbiont of a chlorophyte algae, a green algae, and a Glomeromycotin or Mycorrhizal fungus. A very interesting kind of a plant. The biggest plants, even as far as the Middle Devonian, or the biggest plant-like things, were these tree lichens. It's hard not to call them plants because they look so plant-like. Now, a part of the problem with a reconstruction like this is, did they just grow isolated like that? Well, to investigate that, we need to look at paleosols. We need to look at the rooting structures. What was the density of these individual fossils in two key localities, one in the late Ordovician of Beans Gap, which is here in Tennessee, and another one, which is the late Silurian Bloomsburg Formation, which is at Palmerton, which is actually down here in Pennsylvania. At Beans Gap, there's a whole bunch of these plants preserved on this horizon here. This is the basal Silurian. This is the top of the Ordovician. Here they are. These are the plants that have rooting structures down in through here. And here are the plants here, which were buried by a sandstone. You can see that they're quite dense. Here's a close-up. The paleosol on which they're rooted, which is purple and oxidized, and then the individual trunk casts up into the sandstone above. Here are thin sections showing that fungal structure of lots of tubes. What you see when you look at thin sections of these plants is tubes and spots. All of these arrows show a density of these individual plant-like lichens that were about 2 centimeters in diameter, and clearly formed a closed canopy. Some of them do appear to be branching at the top, and they would have actually created a kind of a closed canopy towering over any kind of early land plant that existed at that time. Here's another locality, which is the Silurian Bloomsburg Formation near Palmerton. And this is a site where Paul Strother found these fragments of Prototaxites here, and also these leaf-like blades. So this particular, he called this the Metaphallus. This was a lichen, which was more like Germanophyton than like Mesellophyton. And here are some of the rooting structures in thin section. The roots do not show a single solid root. They're disrupting the bedding, but there are threads of fungal hyphae which emanate from the base of the plant itself. In these red paleosols, these drab spots are the spots where the individual fossils would have been. This was a plant like lichen, which was almost 3 centimeters across. These were probably fairly tall, about 1 meter or so in terms of their height. And they were spaced at way less than 1 meter. This was another fairly dense stand of lichens, way bigger than lichens that we know today, an extinct group of lichens called the Nomatophytes. Now, there are not too many surprises for me that there could have been fungi or lichens on land in the Ordovician and the Silurian, because I'm the guy who thinks that everybody's favorite Ediacaran worm, Dickinsonia, is also a lichen. I won't develop the idea for this. I've published numerous papers on it. It's still a little bit controversial. I particularly like this example here of this impingement structure of one individual Dickinsonia on another, as if they were just growing side by side. And this is an example of allelopathic avoidance. The main line of evidence, of course, for this is that I found them in paleosols. This is the classic place where you get Dickinsonia in the Flinders Ranges of South Australia, and you get them here, you get them here, you get them here, you get them here, here, and here. These are all different paleosols, which have a sharp top, which have rather massive pedal, by which I mean soil disrupted interiors. They have sand crystals of the sort which we call desert roses, and they are deformed in some cases like periglacial deformation of ice melt. Here's my reconstruction of what the Ediacaran lichens would have looked like on a suite of soils in the late Ediacaran of South Australia. A far cry from the reconstructions that you commonly see in museum dioramas of these as marine creatures. Now, the other thing about Dickinsonia that I've been fortunate to be able to do is I've been able to cut them up. Many curators of museums have considered Dickinsonia such a precious fossil they wouldn't dare cut it up and make a thin section, but I've got a bunch of them in the collections here at the University of Oregon, and there's been no problem cutting them up. They're always chambered. What you see is lots of tubes, including tubes going down into the substrate below. You see a rather thick surface to them, and then there's this system of chambers, and they're similar to a variety of other Ediacaran fossils of the sort which are called vendobionts. I think these are, in fact, early lichens that evolved in the Ediacaran, and furthermore, they continued on into the Paleozoic. These extinct early lichens, probably related to Prototaxites, to glomeromycotans, include this one here, Rutgazella, a species which was found in Pennsylvania in early Silurian age rocks. I was able to collect some more of these too and cut them up. And we see when we cut them up that there are always these rhizine-like things coming out of the base of them. They have a system of chambers, which is very similar to that of the Ediacaran lichens, and they appear to be relatively compaction resistant. Rutgazella this is a reconstruction of it here, is also found with Mesellophyton. Here's a base of a Mesellophyton plant-like lichen. In this particular case, we have the vendobiont, Ediacaran style lichens surviving into the Silurian, as well as the more typical Paleozoic Nomatophyte style lichens. And there are more. One of the youngest of these Ediacaran or vendobiont style lichens that we know of is this form called Protonympha, which is found at two different stratigraphic levels in the Devonian age rocks of New York. Here's one species, Protonympha transversa. Here's another species, Protonympha salicifolia. And look how similar these are to this Ediacaran fossil, which is my personal favorite, actually, Spriggana flounder's eye. They seem to have kind of a basal area here. Some people think this is a head. I think it's a holdfast. And then they have this very characteristic chambered structure, which doesn't quite form a metameric or a segmented form. It's offset. It has a glide symmetry, like many Ediacaran fossils. Once again, I was able to actually cut these fossils up, and I could see that they were, this is the fossil here of Protonympha, and then here's the top of one here covered up by a sediment, but there are these rhizine-like extensions from the fossil down, disrupting the substrate. In this particular case, in the Devonian, these two different Protonympha species were living on land with a variety of other sorts of Devonian land plants, including Lepidosigillaria and including Haskinsia. These were swamp plants in lagoon, levee, and bay facies. Continuing on this line of vendobionts, even when woody plants and other vascular plants had evolved. But by now, of course, the vendobiont body plan, these low ground-hogging forms, was actually overtopped by the vascular plants. Now, there is a record of Dicarian lichens, and by Dicarian lichens, I mean lichens that had ascomycete and basidiomycete fungi, as well as green algae. This is a superb one, which is described by Hoenig et al., including Diane Edwards. They're small charred bits like this, but it's pretty clear these are haustorial hyphae around these photobionts. So this is the mycobiont part of the lichen, and this is the photobiont part. These are way more similar to modern lichens than either the Nomatophyte type lichen or the vendobiont type lichen, which I've just been describing. And then there's this other one, which is kind of a weird one. It doesn't appear to be like any modern lichen. It's a different one altogether, described by the Taylors, Tom and Edie, among other authors. It appears to have a cyanobacterial photobiont, and they appear to have been connected in cup-like forms on the top of the lichen. This is a really weird one, which has been called Winifrenata reticulata. So here we are. By the early Devonian, we seem to have about 4 different kinds of lichens. We have the Nomatophyte type. We have the vendobiont type, which goes back to the Ediacaran. We have the Dicarian type, which is more like modern lichens. And then we have this weird one here, which seems to be not like all the others. Now, probably you thought I was going to be talking about Devonian plants, actual plants. Well, now is the time to start on that. What about trees and other plants in the Devonian? Well, there are 2 main kinds of plants in the Devonian that formed trees. One of them is this woody plant called a progymnosperm, which has the anatomy of a pine tree, basically, but still reproduced by spores. A very interesting missing link in the evolutionary history of plants. The others are what here's a cladoxylalian fern, which has this very strange tree fern like stump. We also have evidence of plants, not only from fossils like this, which are based on permineralized material from upstate New York, but we have evidence of plants from fossil soils in the Devonian. Here's a whole pile of fossil soils here at a very famous locality for tetrapods near Heine in Pennsylvania. Now, how do you recognize a paleosol? Well, you recognize it when there's a sharp top, and then it's all confused looking, bioturbated, pedal, slicken-sided, and then it gets bedded lower down. In this case, there also are calcareous nodules. In this case, here's another one, sharp top with bedding, then it's massive, and then there's nodules. Here's a set of sediments. Here's another one, sharp top at the hammer right here, and then it gets bedded again down here, sharp top right here, and then it gets bedded again further down. What you do to study these sorts of things is you look at their chemistry, and you look at the proportion of clay, silt, and sand. These are two very well-developed soils that are classic for the Devonian of New York and Pennsylvania. A rather shallow calcic one with a BK or calcareous nodules rather shallow in the profile, and one with calcareous nodules rather deeper in the profile, and a lot of slicken sides and other things that indicate that it was a kind of a vertisol, a kind of a swelling clay soil. Now, we can work out paleoclimate of soils from a variety of different what we call transfer functions. For example, that depth to the carbonate, which I showed you in the paleosols, in modern soils, this is modern soils, shows a nice relationship with mean annual precipitation. The chemical index of alteration minus potassium, a chemical index, also shows a relationship with mean annual precipitation. This alkali index shows a relationship not so good with mean annual temperature. So with a few chemical analyses and with some field observations of depth to BK, with a few caveats, of course, we can start to reconstruct the paleoclimate of these Devonian paleosols. We can also get from paleosols the CO2 by studying the isotopic composition of the carbon in pedogenic nodules. And this is because the isotopic composition of the air is -5. The isotopic composition of a leaf is -26. And since the isotopic composition of humus is -24, when the leaves decay into humus, they don't change all that much. And there's a mix of air coming down in the profile. That makes the isotopic composition of caliche -14. The deep soil air can be even more negative. But the idea is, if there is more carbon dioxide diffusing into the soil from the air, that will send the composition of the nodules more positive or higher. And from those ratios, using this formula, we can calculate the amount of carbon dioxide in the atmosphere. The key variable is this one here. We also need to know the amount of carbon dioxide in the soil, which is a function of soil respiration, the decay of humus in the soil itself. Well, we can actually calculate that from the depth to the carbonate in the soil, in the paleosol, and we can correct that for the depth of compaction. We can also calculate it from the depth to the gypsic horizon in the soil. And what we found was really very interesting. This is the stratigraphic level in the Devonian rocks of New York and Pennsylvania, and we found that there was a record of quite striking changes in seasonality, in precipitation, and in CO2. CO2 was high during these episodes here, which are well known from the marine fossil record of this area as times of black shales and of extinctions of marine fauna. It appears that there were CO2 spikes, probably created by volcanic eruptions somewhere else, by tectonic changes, these abrupt spikes. We see them throughout the fossil record. And the response of plants to these spikes was really quite marked. Now, I show those data because here's one of my key slides, I wanted to show, for example, how the size of plants changed through time. Now, this has been done for marine fossils, of course, and this line you can barely see here. This is the increasing tiering of marine fossils. This line is the height of nomatophytes, those tree lichens that I've been telling you about. And this is the height of vascular plants, calculated from the diameter of trunks and other fossil remains. It's pretty clear to me that nomatophytes towered over plants for a good part of their history until about the Middle Devonian. In the Middle Devonian here, nematophytes was still the biggest thing around, and vascular plants were still just a shrubbery. It wasn't until the Carboniferous that we started to get the sorts of trees, vascular plants, woody plants, that towered over even the nematophytes. And nematophytes seem to have been extinguished and replaced by vascular plants. This spikiness is a feature of the record which I used. This is largely a record from the fossils and the rocks in New York and Pennsylvania. And these spikes of productivity and tree size also reflect spikes in CO2 and spikes in moisture and in warmth of paleoclimate. So it appears to me that there was a rather unusual episode in the early evolution of land plants, which was facilitated at first by the presence of mycorrhizae. And then these individual early land plants were in the shade of tree-sized lichens. They weren't tree-sized at first. This is just pencil-sized. This is about 3 meters or so here. Here's one that's about 10 meters or so. These lichen-like, plant-like lichens evidently towered over plants until quite a bit later in the evolution of plants. We can see this especially from the evidence of fossil soils. Fossil soils have relatively shallow calcic horizons. These are the calcareous nodules here, and not too much structure for a good part of Earth history, Cambrian Ordovician. And then the nematophyte lichens come in, and these create a little bit more structure in the soil. And then finally, earlier land plants sheltering under these tree-like lichens. And finally, proper woody plants with deep roots that created the kind of blocky structure and very deep calcic horizon we see in modern soils. So here's my last slide. I know there's a lot of text on there, and don't worry, I won't read it. I'm going to sing it. So where on land would there be shade before trees spread their leafy glades? Prototaxis, tall lichen canopy, towered above the greenery. Those very ancient lichens were fueled by green algae, not the mushroom fungi we still see. Their fungus was glomalien, yet not mycorrhizal internet. Land plants needed both kinds of fungi to survive, moist shade and supplies from fungal drive. Symbiosis allowed survival, then nurtured trees to shade out lichens. And that's it. Thank you.
Aqui, everybody's listen. Let me put here. Are you listen? Everybody's listen.
Yeah. Beautiful song.
Thank you.
You are a good singer, Dr. Retallack. You are a good singer. You are a good singer.
We just saw a documentary on the Bee Gees, and I got inspired.
Okay, okay. Dr. Retallack, let me change the Dr. Retallack. Thank you very much for your amazing lecture. Sincerely, I liked a lot your lecture. And good issue, good topic, sincerely. And we have here many questions to you. Okay, so I don't know if you see this question in chat. If now I will read. You can read?
No.
You can see or no? No? Okay, so I will read.
I can't see the chat, no.
Okay. I want to ask also, but I will ask after. Dr. Marco Gervásio, do you want to ask anything to Dr. Retallack? You have any question? Do you have any question?
I had two questions, but one of my questions, Eduardo make this question, you make these questions. But I would like to know if Dr. Retallack studied histosols, and to histosols, what do you think about the best proxies to demonstrate that was a climate change? Or especially for histosols, do you think there is specific indicators for histosols, or the same indicators used to mineral soils could be used to histosols too?
Oh, yeah. So as I understand it, the question is, what are the best proxies to use to understand paleoclimate and other variables for paleosols? Well, it varies. So when I started, we only had a few that I had invented, but now we have quite a lot, actually. So for paleoprecipitation, there's more than a dozen now. And I put them all in a table in the most recent edition of my textbook. And so it depends on what you're trying to do. So these proxies are invented from looking at modern soils. They're invented, so for example, if you look at the depth of the calcic horizon in modern soils, you want to keep all the other variables more or less constant. The way Hansieni envisaged it, he wanted to just have the Great Plains of North America and look at just loess, grassland in semi-arid to arid climates. I generalized it, but I still kept it so that there were always unconsolidated sedimentary materials like loess or alluvium or even gravel. I also broadened the climate to be independent of temperature. And so my proxy is a little more sloppy than the original one, which was just for loess soils under grassland. But then it's useful for a wide variety of paleosols that you might find in the fossil record. Now, you have this balance between you have to pick the proxy that works best for you. It turns out the proxy that I like best now for looking at the paleo temperature of Precambrian soils is one that was just recently published by a guy by the name of Oskarsson in Iceland. And I like that one best because it does not include a lot of vascular plants. It includes mainly microbial earths and non-vascular plants. So you need to look into the mechanics. These are people who publish these proxies will give you the database that it's based on, and people are also adapting these proxies for a particular purpose. If you wanted to do a proxy just for oxasols, that'd be fine, or just for vertisols. There are proxies just for vertisols, and what you gain for that is greater resolving power, greater accuracy, because you're sticking to one soil type. But then it's not universally applicable to every paleosol you might want to study. The answer is you have to look under the hood.
Okay. Dr. Gregory Retallack, we have more question here. Eduardo from Brazil, Eduardo Neto want to ask, if most present-day soils are the product of soils formation factories that have changed widely over time, cannot they all be considered paleosoil? polygenetic soils, paleosoils?
Yes,
Did you
yes,
understand?
Yes, they are. Yes. Generally speaking, what we consider a moderately developed soil, and that's the sort of soil that we would use a proxy for, would be Holocene in age, around about less than 10,000 years old. Over that time, it turns out actually climate's been remarkably stable. And so one way to eliminate modern soils from developing a proxy is if they are older than that, because then they are likely to have experienced some glacial conditions, and that's going to mess with you. You want to try and keep things constant. You don't want to get polygenetic soils in there. You want to get soils that, and it's rather remarkable actually that in the last 10,000 years that climate has remained so stable. Some people even argue that that's because of humans. That humans kept the climate stable by agricultural release of CO2, which undid the advance of the next glaciation. But yes, a soil that is at the surface and that formed in the Miocene, like you have in Brazil, that is a paleosol. But it's not one that I'd like to interpret the environment of, because we don't know exactly what age we're talking about. It could be any age between the Miocene. It's basically accumulated all those episodes of soil formation. But if you stick to the Holocene and you stick to intervals of about 4,000 or 5,000 years for each paleosol, which seems reasonable, when we look at the size of the nodules and the degree of development of soils, then we're looking at the development there.
Okay. Dr. Retallack, Eduardo has another question. First, he said, thank you for your presentation. And he asked, I would like to know what you consider to be the main changes for the study of paleosoils in tropical areas.
The most soils in tropical areas? Oh, the classification?
Yeah.
Oh,
yes.
There's the best classification by far on a global basis is the food and agriculture classification, and I think
Shelley, I will ask again. Maybe my English is not good. I will ask again. I would like to know what you consider to be the main changes for the study of paleosoils in tropical areas. Changelings. You want to know? Yes, sorry. Please, Dr. Gervasio, if your English is better, you help me here.
I have studied soils in tropical areas. I worked for some time on paleosoils in Kenya, I like to use classifications that are appropriate to them. I like the FAO classification better for them. The US classification is rather poor on them. Oh, the main challenges. Oh, in tropical areas.
Yes.
Challenges. Thank you.
Yes.
Well, they're covered up with green stuff. Speaking, you've got very little outcrop, it's kind of that's the biggest problem. Finding outcrops to study paleosols in tropical areas is difficult, and that's why I headed to the rift valleys of Kenya. But there are I would consider parts of India fairly tropical as well. You can still get a lot of erosional badlands, and the other thing that's really worth looking at are drill cores. It's very easy to recognize paleosols in drill cores. And many tropical areas that have been explored for oil and gas have a lot of drill cores, mainly into marine rocks, I know, but sometimes they include really nice paleosols.
Okay. Dr. Natalia Zaviolova, she's asking why we do not see giant lichens in later epochs.
Yeah, I think they were shaded out. I think they were basically outcompeted. Now, I've written about this in my paper on Prototaxis. The growth rate of those lichens would have been really quite slow. compared to vascular land plants, probably an order of magnitude less. And so it's all a question of shade, as in my song. I think they just got shaded out. I am surprised, however, that there do not appear to be any, well, there is a glomallion lichen. It's called geosiphon. It's a tiny little thing, and it has a very different form of lichenization. It includes Volvocalian cyanobacteria in a vesicle inside the cell itself. It's a really weird little thing. It's found in a few places in the forests of Germany. But yeah, these kinds of giant lichens, and geosiphon is a plausible ancestor of the Vendobian type lichens. They've been on the run since the Middle Devonian. That's when they seem to disappear.
Okay, okay.
I
think one more question.
Oh, yeah.
I think so.
Yeah.
Oh, no, you can continue. Do you want to continue answering this girl? You can continue.
Yes, yes. The ones that are on the screen are easy to read. Yeah, how can paleosols be classified? Well, they can be classified in modern classification systems, I think. Now, I know some soil scientists think this is heresy, that the classification was designed for modern soils only. But it's all a question of proxies. I'm a paleontologist, and I have no difficulty identifying a fossil snail, a fossil land snail even. Now, we know that you can't identify modern fossil land snails unless you can dissect the penis. In other words, you have to do a live dissection of the animal itself. So theoretically, it's not possible to identify any fossil land snail. However, we also know that land snail specialists are not always dissecting penises. They often just identify them based on the shell itself, which can be quite characteristic. We're now developing a whole bunch of proxies. My colleagues at Baylor University, Steve Dreesy and Lenoort, have devised a number of chemical proxies for pH, EH, linear extensibility, and a whole bunch of classic soil features, even for cation exchange capacity. These are things that we can get through proxies. They're mainly geochemical proxies. So what you lose when a soil becomes a paleosol is you lose the whole cation exchange complex is gone. So all those reactive surfaces are now squashed and just dead. But what you do have is a bulk soil chemical composition, and you can look at the profile bulk soil composition from the top to the bottom into the parent material, and from that you can reconstruct what kind of a soil it is.
Okay, okay. So I want you to ask you one thing, and Francisco Silva from Brazil also. I think my question is similar his question. For example, when you are in a field and you see outcrop with many beds, with many stratus, how can you identify a paleosoil? So I will put the Francisco question here. Please explain a little bit more in practical terms how to differentiate distinguished paleosoil inside a sedimentary sequence.
Yes.
Usually not very easy task.
Yes, it is difficult to identify paleosols inside sedimentary sequences, and I still see papers published just last week of sequences that have paleosols in them, and no paleosols were reported. So paleosols have three things that distinguishes them: root traces, soil horizons, and soil structure. Now, root traces don't help you in the Precambrian, but you've still got soil horizons and soil structures back there. Root traces are easy to pick out. They branch and taper downwards. They look woody. They have kind of a characteristic surface texture. You can look at them in thin section. You can excavate them out. They're really pretty good. The bit that most sedimentologists don't get is the soil horizons. The BK horizon, the calcic horizon, the gypsic horizon, the argillic horizon, the clay-enriched horizon. And for that, you have to tune into looking at slicken sides and degree of clayness, sometimes even taste the rock in the field. And soil structure, this is the part that most people are completely at sea with. Soils have a system of cracks. And those cracks have different sorts of names. We call them cutans. And the cutans can be altered in different ways. They can be oxidized, they can be lined with organic matter, they can be leached. There's a whole terminology for these things that when you cue into, you can understand. And then those cracks define a unit of soil structure, a clod, which is called a ped. Now, you might think, oh, the clods of soil, there can't be anything to that. But just think how different soil peds are in different kinds of soils. If you dig under a grassland, all the peds are tiny little crumb-shaped things about the size of a grain of rice, and they run out between your fingers. In a forested soil, like a temperate forested soil, the peds are sticky and angular and blocky and have quite strong silicon sides around them. There are different ped structures for different paleo environments and different kinds of soils, but you're not going to see them if you don't know what you're looking for. And that's been true for a lot of sedimentologists.
Okay, Dr. Gregory. Thank you very much. I don't know if you have already answered Dr. Natalia Zavialova. What about disturbed area? I think you have already answered or not.
What about disturbed areas? Yes. What about disturbed areas? Well, the whole fossil record is disturbed areas, pretty much, because I'm largely dealing with paleosols that are in sedimentary sequences. And so the disturbance is the sedimentation. So there's this yin and yang thing going on, okay? So the yin, the conserving, the building, the constructing aspect, that's soil formation itself. And the yang, the destructive part, is the flood, the hurricane, the mud flow, the lava flow that is covering up the soil. And so you have this alternation. They are all disturbed areas. Now, there is an exception to that, of course. There are other paleosols, and many people have concentrated on these paleosols that are at major geological unconformities. And these paleosols are often tens of meters thick. These were undisturbed areas. These were thick upland soils that developed perhaps for millions of years. Now, there's a problem, of course. If a soil develops for millions of years, then how can you characterize the environment over a million years? I prefer the ones that are disturbed on a timescale of just a few thousand years, because then you've got the environment and how the environment changed on that 1,000-year timescale. The million-year ones, of course, are a concatenation of a lot of things happening over a long period of time. And they don't give you any resolution for a paleo-environmental record. I really like it when we can start to get paleo-environmental records of greenhouse spikes, for example, like the ones I showed you in the Devonian of New York.
Okay. So thank you very much for your answer again, Dr. Gregory Retallack. Let me talk some things in Portuguese. Bom, pessoal, muito obrigada pela presença de todos em mais uma palestra. Eu quero deixar claro aqui que estou muito feliz com a presença do professor Gervásio também aqui, né? E que, na verdade, isso é um projeto de extensão, né, professor, da Universidade Federal Rural. E assim, eu espero que nós tenhamos mais palestrantes, né, de diversas partes do mundo. Hoje em dia o mundo é globalizado. Eu estou até falando em português, mas o ideal era estar falando em inglês mesmo. Nós temos que começar a nos habituar à ideia do inglês, porque a globalização está aí. E a ciência é globalizada. So, Dr. Gregory, it's an honor for us receive you here in Brazil, in Rural Federal University of Rio de Janeiro. Really, nowadays, the science is globalized. Globalization is nowadays, okay? So we have to do works together, to do good presentations with many scientists from different parts of the world. So it's an honor you here. So for my terrible English, I don't have a good English, but I try. I try. I think you understand me. Okay? I knew Dr. Gregory Retallack in Birbalsan Institute of Paleoscience in India. I think 8 years ago, I think. In 2013, I think. Yes, in 2014. Dr. Gregory was there. I remember Dr. Gregory there.
Yes, I'm sorry you missed out on the trip to Khajuraho. That was fantastic.
Yes, Khajuraho.
Next time you go, you need to take in Khajuraho. It is epic. That's beautiful.
Yes, I'm sorry, Dr. Retallack. I couldn't go there. I liked it when Dr. Retallack was there, because when Dr. Retallack was there, I ate meat, because in India it's difficult meat. Meat is difficult. But when Dr. Gregory Retallack was there, I ate meat. Because important scientist, he saved meat. Sarah no. Sarah was not important, so no meat there for me. But when Dr. Retallack, Dr. Xixiao, when Xixiao was there, I was very happy also. Because meat for him, so he saved meat also. Is it? So is it?
Birds. Yes.
Yes. Dr. Gervásio, you can say your last words to grateful Dr. Retallack. Okay.
I would like to thank Dr. Greg Retallack to accept to join with us for this lecture. And I decided this is the start of the a partner to join together with tropical soils, because there is a lot of things that I think could be make here in Brazil.
Yeah.
Thank you.
Yeah, and you have wonderful paleosols in Brazil, particularly in some of the Permian and Ediacaran basins. There are really lovely Ediacaran paleosols in Brazil.
So I will think about this, and in the next opportunity, I will try to make a new project and invite you to join with us to participate in the project.
Yes,
well, thank
yes.
you.
I'm very honored.
Very good idea, Dr. Gervásio. Very good, very good idea. I like it a lot. I like it. I want to grateful for everybody that is here. Watch this lecture. Thank you very much. Everybody's here. Ask Dr. Laura Lima, Natália, Eduardo, Francisco Silva, Eugênio Neto. Many people are here in this presentation. Jailane, okay? So thank you very much for everybody here in this moment. Okay, Dr. Retallack, I will provide a certificate for you. I will talk to Dr. Gervásio after. Okay, PDF certificate, and we will send it to you.
Yeah, that'd be lovely. Thank you. I would like to share it on Facebook.
Okay, and please, you are welcome to Brazil. Okay, you come here to visit us.
Thank you. We good?
Yes. So bye.
Bye.
Bye.